Continuation of aromatic compounds. We looked at last quarter what are aromatic compounds, how do you decide whether something is aromatic or anti-aromatic or non-aromatic, and all of that stuff we did. Now in chapter 16 we are only talking about benzene and benzene reactions of benzene and so on and so forth is what we are starting in chapter 16. Did we already learn how to name benzene compounds? We did.
Yes.
Yeah. So, there are a few reactions of benzene that we will go over in this chapter. But let's start from, maybe I'll finish this first and then I think that's a bit late. Okay. So, do you all remember what is benzene? Anybody?
A cyclohexane with 3 double bonds.
With 3 double, with 3 double bonds.
Yep.
But it's not a triene. Let's not, please remember, cyclohexatriene does not exist because cyclohexatriene is the correct name for that is benzene. Isn't that right? Aromatic, yep. For the reasons that we've discussed before. The chemical formula is C6H6. Can someone tell me what is the hybridization state of every carbon in benzene?
sp2.
So what should be the shape of the whole ring? Okay, what's the shape of every carbon?
Shape at every carbon is trigonal plane.
Trigonal planar. So if every carbon is trigonal planar, what is the shape of the whole ring?
A planar ring.
Planar ring. The ring is completely planar with all the bond angles close to 120 degrees. In fact, if you really think of, and I'm going to try my artistic skills, which you know are way above par. Spring break, we forgot how to laugh. What? That's not fair. Okay, sp2 hybridized. How many hybrid orbitals does an sp2 hybrid atom have? Anyone? 3. And what kind of bonds do hybrid orbitals make?
Hybrid orbitals make sigma bonds.
Sigma bonds. So that is why each carbon is sp2 hybridized with 3 sigma bonds. And then what else does an sp2 carbon atom, sp2 atom have besides the 3 hybrid orbitals? What else do they have?
A pi bond.
P orbital, which is perpendicular. So each of the carbons has also an unhybridized p orbital. And what do those unhybridized p orbitals have in them?
Electron.
1 electron each, because if you write out the electron configuration and all of that, it would be like, oh, each of them has a single electron. And basically those are the ones that are being delocalized to create the resonance delocalization. The ring itself, though, is planar. If you look at the 6 carbons and the 6 hydrogen atoms, all 12 of those atoms are in the same plane. Do you guys agree? Mm-hmm. Everybody?
Yep.
Okay, cool. So this is also hopefully a review. Do you remember what does the term benzylic mean?
A carbon away from a benzene ring.
So a benzylic position, which can either be a carbon or whatever. The point is, yes, absolutely, it is something that is attached to a benzene ring, not on the benzene. I mean, it's not part of the benzene ring. So if it's a carbon atom, then this carbon is the benzylic carbon, and of course, hydrogen is hydrogen on that benzylic or whatever it is. But that's the benzylic position, which is on the benzene ring, but not part of the benzene ring. Okay, cool. So the first reaction that we are going to learn in this chapter is oxidation. Actually, let's start with something we know. We've already learned before, so it's more of a review, sorry. Let's do a reaction that we've already learned first. Benzylic bromination. You guys remember this reaction?
Yep.
What is reaction, anybody?
Uh-uh.
What's going on in this? You said? Yes. Sorry,
A
Prince.
bromine is added to a benzylic position.
Okay,
with
bromine is, when you say, am I adding, what kind of a reaction is it? Okay.
Oh, substitution.
Substitution. So one of the hydrogens on the benzylic position is being substituted by Br, right?
Mm-hmm.
Yep.
What is being used for benzylic bromination?
NBS.
NBS is one of the better reagents to use, although, of course, since the benzylic free radical, it's a free radical mechanism. Since the benzylic free radical is pretty stable, it can also be bromine, but NBS is definitely used. You do need heat or light because it is a free radical mechanism. Does everybody remember that?
Yes.
Yes? Okay, so please tell me. Please tell me what would be the outcomes. Just complete the reactions, basically. So what would be the first product?
Wouldn't it be
What would you write here?
2, 3?
1, 2, 3.
1 bromo, 1
Two.
phenol, 1 methyl, and then propane.
How about 2 bromo?
2 bromo,
phenol,
2 phenyl, butane.
Longest continuous chain of carbons. We all agree?
Yep.
Okay. So now that's what kind of an alkyl halide is that? Primary, secondary, tertiary.
Tertiary
So
benz.
now we have a leaving group. Isn't that right?
Yep.
Okay, so what would be the outcome when this product reacts with water?
Oh yeah.
What mechanism? Elimination, but water is not a base. Substitution, which one?
SN2.
SN2, why? That's tertiary.
SN1.
What would be the outcome?
OH on the PR.
So an alcohol, right? Now this mechanism you should be able to write because we have spent considerable amount of time on SN1 reaction, carbocation, blah, blah, blah. Everybody agrees?
Mm-hmm.
Okay, same alkyl halide now reacting with sodium methoxide and heat. So what reaction would that want to go through?
SN2?
E.
Oh no, E2.
It's
E2.
tertiary.
E2.
So E2. So what would be the product? And E2, how many different alkenes are possible, but what would be the major product? Major would be
I'm inclined towards the ethyl group.
meaning the Zaitsev's product.
Yes.
Why? Because
Small base.
small base, not bulky.
Mm-hmm.
You all agree? Do you remember this from
Yes.
last quarter? Okay, same thing but with potassium terbutoxide. So this is E2. Should be able to write mechanisms, guys.
Hoffman's product?
The Hoffman, and what mechanism is it?
E2.
Also E2, but this time because it's a bulky base, the proton will be taken from the less substituted carbon, giving us the Hoffman alkene. And then what about with ethanol? What would that be?
SN2.
But it's a tertiary alkyl
Oh,
halide.
SN1.
Tertiaries cannot do SN2, so
Sure.
still
Yeah,
SN1,
as we
but
remember
what
from
would be
last
the
quarter.
product?
Ethoxide? No, not, sorry.
Ethoxy.
Ethoxy.
And epoxy.
And of course, please, should be able to write all these mechanisms. Does that make sense, everybody? Okay, so let me write a few more, and then maybe you can take a couple of minutes, not more, because you've already done this before, and complete. The question is the same, complete the reactions. Whatever is missing, just add that. Irene, bless you. Okay. Please take a couple of minutes. Let's finish these reactions. Basically, whatever is missing, we have to provide that. And I'll be right back. Feel free to talk to each other, work together.
Okay. First one, NBS. Benzoic bromide.
So MB is
NBS puts a bromide on the benzoic position.
but that's not a benzylic.
Yes.
How did you just put the bromide?
I just put it on the primary benzoic position because that looked like it was the only position available.
So you get an H from the CH3.
And then sodium cyanide. We're using cyanide, so it's SN2. SN2 substitution.
Let's see if you got the same.
Since it's a primary now.
Ah.
One. T-bute oxide and heat. MCPBA results in an oxide.
Let's see, do we have the same? I did the second one. I mean, yeah, the second one.
I did a MBS because we need to put, MBS because we need to put something here that we have to eliminate. And
I
then
put NaOET.
we don't use F oxides for Hoffman products. We use T-butoxide.
Oh, that's right. That's a Hoffman. So T-bute
Yeah.
and then heat. Is that what you get? But why do you? Oh, because duh.
Something that we need to take off.
Of course.
Pills are also not just
And then did you get this at the end?
the active ingredient, right? There's a whole different
Oh, you haven't done the
process.
end?
I haven't done that yet.
Okay,
Let's
check.
just say
That doesn't-
ibuprofen, for example.
That doesn't
If you look at the back of
MCPBA.
boxes,
If I'm
it
right,
has
that
a
yields an
list of active
epoxide.
ingredients and inactive ingredients.
You're right. You are right. I got confused with the one that takes out the, yeah.
Yeah,
Thanks.
trying to go back through my notes for last quarter.
No, you're right. You're
I'm
totally
glad I
right.
got one of these notebooks.
Okay, just go like that and then
Synthesis,
ethoxide.
alcohols,
There are
and
quite a few good ones out there, actually, and not too complicated
oxidative
ones.
Okay, so then
flavors.
this one gets, okay. And then,
Yeah, to get an epoxide, we use MCPBA.
yeah.
So we, so if we did MCPBA,
You get this.
yeah, we would, we'd get something like that.
And then you
Visible, so you
take
can
it,
do
this
it.
one goes to the less substituted, right?
Which is the trickiest
Less
part.
substituted
Yeah.
or not? Or more substituted? I think the less.
So drug in the drug
Trying
sense of
to,
the word, or just the generic any.
Trying to circle back through my mind from last quarter. Not too easy.
1, 2, 3, 1, 2, 3.
We did an epoxide and then we reacted it with Grignard's. That type of reaction seems to look unfamiliar. Getting the epoxide and then we react that with Grignard's.
The trickiest part, when did you guys start thinking about it?
Mm.
When we first brought it up, but the pressure's been kind of low.
That's what happens, right? It's due tomorrow, so I'm gonna do it tonight. Because the reason I'm bringing it up is because the trickiest part is to find something that A, can be done in this amount of time, B, can be done with the resources we have. I mean, forget about the chemicals and all. Even in terms of the lab facility, there's only so much we can do. Last year, was it last year, Kate? No, was it the year before? Kate and Micah, they made a
what is it?
disaccharide. On
What?
paper,
What
that's
was
a
it?
one-step arrow kind of a process and done.
Was it
and,
this?
It
And
took
then
4 weeks
do
and
we-
stuff. And even then,
Would
we
we
don't
take
really know if
these?
we have it. We
I
just have
guess-
to
something
the
less-
that
less
looks
substituted or
different
more
from what you
substituted?
started with because you don't have
Well,
instrumentation
both of these have
to
two-
do that kind of
two-
analysis, right?
This has a hydrogen on
Ion
it,
and mass,
but that
easy
doesn't-
mass
but-
and all of that stuff. So it
That-
makes
So
it
they
a bit
break.
limiting
One of these is
that-
going to break when
Yeah,
this
one of the
comes
bonds
in.
breaks. But which bond breaks?
Is it the less substituted?
What tools?
You have it in your notes?
They might have contacts at Nuda. So
Oh,
that is a great tool.
nucleophilic
yeah.
R.
If you have contacts at
That's what
Nuda,
Grignard has, so it serves as a base.
which I also have a
Yeah, but
She was about to trip us with this.
Yeah, but we're-
Right, because you gotta have this done before say, which is June, whatever that day is, before the science exhibition, right? So you can present your work. Okay, keep thinking. Yes, oh, sorry, I got distracted. Are we done?
Base catalyzed
So
goes
what's
to
the
the more
product from the
substituted
first one,
carbon.
anybody?
More substituted?
The product
What should I write here? Okay, what is NBS doing?
It
A
puts
BR.
it puts a bromide on the benzyl
Bromine on the where?
on the benzylic
Do you
position.
guys agree?
Yes.
So what's going on with sodium cyanide?
A substitution.
What kind?
SN2.
SN2. You're just doing an SN2 reaction because that's a primary, this is a primary position. That's a good nucleophile SN2 reaction, and it's just putting a cyanide group there. Everybody agrees?
Yep.
Okay, next one. What do we need to convert this ethyl benzene into styrene?
Since it's
First we use NBS.
Okay, if we use NBS, please make sure when you're using NBS, you either have heat or light, because it is a free radical mechanism, so you need to have energy to initiate the process. Okay, and then?
We use a bulky base,
But in
T-butoxide.
this case, does it matter whether it's bulky or not bulky? Because once you get this compound, there's only one direction to do elimination in.
Oh.
Too strong base.
So what would that strong base be?
I put any.
You can use, but please remember that E2 dehydrohalogenation takes an alkoxide ion.
Okay.
Is better, and of course the size of the alkoxide ion will decide whether you get the Zaitsev's product or Hoffman's product, but in this case there's no other option. So yes, absolutely, you could use sodium ethoxide, sodium methoxide, sodium tert-butoxide, any of those is okay, because there's only one way to go. So you can, with heat of course, because you're trying to do elimination, or sodium ethoxide, or tert-butoxide, anything is fine as long as it's an alkoxide ion.
okay.
Sodium hydroxide is not, because sodium hydroxide there's going to be a danger of substitution as well, so maybe use one of the alkoxides. Okay, but then once we get the alkene and then do steps 1, 2, 3, what's the outcome?
Epoxy.
Stop.
That's giving an epoxide, but then what about 2 and 3?
Yeah, then
Mhm.
you send it to the less substituted, the
So what's the final product? You're right that step number 1 will produce an epoxide, this one. And then the Grignard goes to the less substituted carbonates, and then of
So
course,
so
step 3, so what's the product?
it's OH in the
OH will be here.
yeah.
Yeah.
And then the
I'm
second
adding
one
1, 2, 3
1, 2, 3.
carbons, so 1, 2, 3.
Yeah.
Did I do that right?
Yeah.
Everybody okay? Okay,
1,
next
2,
one.
1.
What's the product after step 1, 2, 3, 4? So that's, step 1 is basically putting a bromine in the benzylic position, right?
Yep.
And then, what's happening in step 2? What's the outcome of step 2?
Double bond
Hoffman's, right?
Hoffman
Because you want a
product.
bulky, so this one, am I right?
Yes.
Okay, now
Yeah.
ozonolysis. So ozonolysis means the double bond will break, right?
Yep.
So what happens to the main part? That will become a ketone,
You get a formaldehyde.
and of course you get a formaldehyde too, absolutely. You're absolutely right, we'll also get formaldehyde. Everybody agrees? Okay, so let's just consider the ketone for now. What if this ketone were now being reacted with sodium borohydride and methanol? What does that do? What does sodium borohydride do?
It's a
It's a source of hydride.
Okay, good, it's a
Hyd-
source of hydride, so what will happen to the ketone?
It will become an alcohol.
Will become an alcohol. Which kind of alcohol will the ketone become? Primary, secondary, tertiary?
secondary.
It's a reducing agent by providing a hydride ion. We did the mechanism of that reaction also last quarter, so please make sure you can write the mechanisms. Okay, what about the same ketone now reacted with phenylmagnesium bromide followed by protonation? So what would that give us?
An alcohol, but adding the pH. Oh, sorry, the pH. I'm
Got
just
it.
reading my
Phenyl.
phenol group.
Oh, that is pH. I got it.
Adding another phenyl.
The mechanisms for both of those are exactly the same. The difference is that sodium borohydride is providing a hydride ion. This one is providing a phenyl, electron-rich phenyl group, but it's the same exact mechanism.
Mhm.
You guys good?
Yep.
Cool. Any questions? Okay, so the next reaction of also the benzylic position, so to speak, is the oxidation reaction where, let me write it first. If you have an alkyl side chain, it can be oxidized by using a very strong oxidizing agent. So this one we haven't done before. So if you have any alkyl group on a benzene ring, we can use a strong oxidizing agent where the ring the side chain, the R group totally disintegrates and leaves behind benzoic acid. All other carbons become carbon dioxide and water because it completely disintegrates. All carbons, hydrogens oxidize to carbon dioxide and water except for the benzylic one. The benzylic carbon, the carbon that was directly connected to the benzene, becomes carboxylic acid. And this R can practically be anything. R can be anything except there is only one exception. And that is a T-butyl group. T-butyl group for some reason is immune to this reaction, does not undergo anything when this reaction happens, it stays intact. But otherwise, R can be anything, any alkyl side chain, and it will undergo this reaction. But we need a strong oxidizing agent. So the strong oxidizing agents, the strongest actually is chromic acid. Chromic acid does not, cannot be stored. It is extremely strong and very, very toxic as well. So we created by taking sodium dichromate and adding it to sulfuric acid. So when these two come together, they create chromic acid. And chromic acid is an extremely strong oxidizing agent, very strong. Red fumes, it looks pretty scary. I kind of want to tell you a story here about chromic acid. So when I was doing my master's in India, this is way, way, way back when. So I'm sure, I hope things are different now. Well, we used to pipette with our mouth, so.
Rick told us that.
I know it's common. I mean, you had a sip of sulfuric acid, who cares? Just go on. Anyways, but in terms of this, our organic lab, we didn't have hoods and things. We had none of those things. This was master's lab. But yeah, our organic lab surrounded a courtyard area where people would, students, everybody in the lunchtime enjoy sunshine, eat food, and blah, blah, blah. We used to clean our glassware with chromic acid.
No.
We actually used to take sodium, which is beautiful orange crystals, and take concentrated sulfuric acid, which is fuming, and add the two. Yeah, you got beautiful orange, not beautiful, pretty scary, red fumes of chromic acid. And we used to clean our glassware with that. No, we didn't have gloves. Goggles? Who cares? And we didn't have hoods. So our teacher, our professor had told us, when you want to do that, just go outside and do it. In the courtyard. Yeah, of course, so we would just do this in the courtyard. People are milling around, eating their lunch or whatever, and here we are creating chromic acid, cleaning our glassware with. I still remember those days. So the point is, it's actually pretty dangerous. It's pretty toxic. It's definitely a very strong oxidizing agent. If we ever had, we don't have it, by the way, in our lab. We don't have sodium. I don't think we have sodium chromate or dichromate in our lab either. But yeah, it's an extremely strong oxidizing agent. I blame everything that's wrong with me. I blame it to my
Those days.
life as a chemistry
Those
person.
days.
It's like, come on, what do you expect? Anyways, nothing's wrong with me. I'm totally normal, by the way. Nobody laughed. That was kind of fun. Stop it. I need to bring chalk just to throw at you. I miss those days, chalk days. You guys don't even probably know about it, right?
My mom was still shopping.
Yeah, you guys have lived in whippy days.
True.
Chalk days were fun.
And the,
Teachers used to actually
but not
throw.
the, how do you call the eraser?
Yes, yeah, they used to throw erasers at us. Okay. Nobody throws pens at you, because we'll get sued if we did.
I was a good student, so I didn't get one.
I was a good. UW still has a few chalkboards left. Anyways, coming back though, chromic acid is one of the options, and another similarly very strong oxidizing agent, which we sometimes don't take seriously enough, is potassium permanganate. Potassium permanganate, especially if you have it under basic conditions, will be a pretty strong oxidizer as well. So you got to use it carefully. But can someone tell me what family is this guy? Hopefully don't take too long. This guy, what family is this?
Carboxylic acid.
Acid, right? Carboxylic acid. Isn't that right?
Yep,
And what did we use here?
a base.
So, if you're creating a carboxylic acid in presence of a base, will you get the acid? What will you get instead?
Carboxyl.
Carboxylate, meaning it's conjugate base. Isn't that right?
Yep.
Because this base, as soon as carboxylic acid is created, this base can take that proton. How do I put the proton back? There you go. Let's just do an acidic workup where you neutralize the base and put the proton back on it. So therefore we need a separate step to acidify everything back because we want the acid. Does that make sense, everybody? With me, everyone? Okay, so no mechanism needed here either, just knowing the reagents is enough. Let's at least try out a couple of examples to get a slightly better understanding. Okay, so. So as I said, the R can be anything except T-butyl. T-butyl is the only one group that does not do anything. It stays intact. Please tell me what will be the products in each of these reactions. Someone tell me what will be the product. And we don't care about the carbon dioxide and the waters because I mean that's not organic. What will be the organic product for the first one? Which one? So it is this portion, the benzylic position with the benzene. This portion becomes the carboxylic acid.
Oh.
That's it.
So-
All other carbons become carbon dioxide, who cares? All other hydrogens become water, who cares? It's the benzylic carbon and benzene, they together become benzoic acid. That's it, nothing else. You guys agree?
Mm-hmm.
What about the next one? What do you think?
T-butyl, so
So,
it doesn't, it's immune to the reaction.
exactly. T-butyl group is the only group, only R that does not undergo this reaction. So there is no reaction, nothing happens, no changes. Exactly. Okay, what about the next one? What's the product for the next one?
The carboxylic acid.
Which one though? Be very specific.
Benzoic acid.
Benzoic acid, exactly. Nothing is changing here, guys. It's the benzylic carbon with the benzene ring that becomes benzoic acid. Everything else becomes carbon dioxide and water. But the organic is just that much. Okay, what about the next one? Now there are two R's on the benzene. So what will be the product? How many benzylic carbons are there?
2 benzoic carbons.
There's a benzylic position here, there's a benzylic position here. So which one will become the carboxylic acid?
I would
Both.
say, oh, both?
Exactly.
Both.
There's no selectivity here. There's no primary versus secondary. That doesn't exist here. So basically, both will become carboxylic acid. So therefore, what's the product? It's not benzoic acid because, of course, there are two acid groups. No, this is phthalic acid. It's totally different. We haven't named it, but yeah, both of those become carboxylic acids. Make sense, everybody?
Mm-hmm.
So then, what about the next one? All of them? Did I hear all of them?
2 of them.
2 of them. Which one will not?
T-butyl.
The T-butyl.
Exactly. The T-butyl is resistant. It's immune to this reaction.
Is that because it's bulky?
I'm not 100% sure why, to be honest, Mark. I don't really know. It could be because of its size, but there are other bulky groups that do, so I'm not 100% sure. So yes, the T-butyl group stays intact. That does not react, but all others disintegrate, leaving behind a carboxylic acid group. Make sense? Okay, so
Yep.
what's the product for the next one? Anybody?
Again, 2 carbox.
Two
I mean,
carboxylic acids?
Yeah, one up and one down.
Exactly, because there is a benzylic position here, there's a benzylic position right there as well. Exactly, everything else just disintegrates away, oxidized completely to carbon dioxide and water, so basically leaves this behind. Absolutely. Everybody okay? So this is the oxidation at the benzylic position. Questions? So far the 2 reactions we have looked at are both taking place at the benzylic position, either brominating at the benzylic position or oxidizing the benzylic position. Now the rest of everything we will do in this chapter is not on the benzylic but on the benzene ring. And that is reactions of the benzene ring. Things we can do, reactions we can do on the benzene ring. And the 2 primary reactions that we will spend considerable amount of time on and get into the details of, you tell me, give me a second, let me draw it out, and then I'll ask you the question. let's say if you have, something attached, I'm just going to say G for anything, it can be anything, it can be R or CN or OH or whatever, some group on it, whatever that group is. And then it can do one of two things, can either react with an electrophile. Is electrophile electron rich or electron poor?
Electron poor.
Okay, so if electrophile is used and that causes substitute, oh shoot, that was going to be my question. Okay, is this addition, substitution, elimination, or rearrangement? Did I hear a rearrangement? Is that what I heard?
I was joking.
Okay. Please don't scare me that much. Okay, so what is it? Is
Addition.
is it addition?
Oh,
Yeah, it's just like addition.
It's substitution. What are we substituting?
And a hydrogen,
Is it a hydrogen?
a proton.
Proton. A hydrogen minus the electrons. Isn't that right?
Mhm.
Because something electron poor came in, so something electron poor should be kicked out to make use of it, to make space for this. Exactly. But please notice G was not affected. The group, whatever that group is, stayed where it is. It's the electrophile that pushed out an H plus from one of the other positions and took its spot. This reaction is the one we will spend a lot of time on. Most of the time for chapter 16 will be spent on this reaction. It is called electrophilic. Aromatic because it's on the benzene ring. Substitution reaction. Right? Another reaction that we will spend some time on is also on the benzene ring, but instead of the electrophile reacting with the benzene ring, a nucleophile comes in. And the nucleophile does not substitute H, because H has to leave as H plus. H minus is a bad leaving group because it's such a strong base, so it can't be H minus. And H plus cannot be substituted by something that's electron rich. So this is a reaction where the group, whatever the group is, and we'll look at that, is substituted by the nucleophile, and of course the group, whatever that was, is kicked out. This reaction is called nucleophilic aromatic substitution reaction. It's not SN1, SN2, by the way. And we look at the difference with what the mechanism is, but this is nucleophilic aromatic. It's on the benzene ring, which is SN2 hybridized. Did I just say SN2? I'm so sorry.
SP2.
SP2 hybridized, absolutely not SP3. So this is nucleophilic substitution, but it's not SN1 or SN2, because remember SN1, SN2 happens only on SP3 hybridized carbons. This is a very different mechanism, and we'll look at that a bit later. So the aromatic reactions that we are talking about in this chapter are going to be electrophilic aromatic substitution, where an electrophile, which is electron poor, replaces one of the H pluses. We look at those mechanisms, and then the other one we look at is where a nucleophile replaces a leaving group and gives us a nucleophilic aromatic substitution reaction. We look at that mechanism as well. So we will of course start first with the electrophilic aromatic substitution reaction, and once we've looked at that in some